And greetings once again, my AP Calculus AV friends, Mr. Record here from Avon High School, and we are going to start a new topic, 1.5 in our AP Calculus curriculum that's entitled Determining Limits Using Algebraic Properties. I'm going to try to spell algebraic correctly. How's that? Hello, once again, my AP Calculus friends. Mr. Record here from Avon High School, and we're looking at our first video from topic 1.5, which is all about determining limits using algebraic properties. And whenever I teach this particular topic to my students, I like to throw that twist in that really starts to focus on some of the most difficult limits you're going to encounter. And that's where this video's series for 1.5 is ultimately going to land at. I'm going to try to walk you through it slowly, but eventually we're going to take a look at some of the most challenging composite limits and some of the limits that involve products and sums that you could see on the AP Calc multiple choice questions. So without further ado, let's take a look at this topic. We start with some properties of limits, of course, and I want to predicate these properties by saying that B and C we are going to declare to be just nice, normal, real numbers, and N has to be a positive integer. We'll probably look and see why that's the case here in a little bit. F and G are functions, but these two functions have something kind of special going for them in that the limit of f of x, if x were approaching c, is going to give you an answer of L. And let's say that the limit of g of x, let's use a different color there, be better. The limit of g of x as x approaches c is going to be k. So L and k are the two limits respectively. Now, 5 different properties are going to be kind of brought to use here throughout the rest of calculus. And honestly, there's only going to be really a couple of them that I'm going to focus on in this particular example. And that's the two that I'm going to look at first. And the first property is this number 2, the sum difference property. And if you had never ever in your life been exposed to this property, it's very likely it's a property that you would assume to be true. And it's basically saying that if you're taking the limit as x approaches c of 2 different functions that are either being added or subtracted, right, one or the other, then the result is what you would get if you just took the limit of f and separately took the limit of g and just either added them or subtracted them, depending on what the original sign is. And that's our sum difference formula. There's really nothing more to it than that. Now, although property 3 isn't going to be a feature of this particular video, it will be in some subsequent videos, that seems to be following the same logic. The limit of a product of functions is just the product of their two respective limits. And why not extend it to property 4 for the quotient? The limit of a quotient is just the quotient or the division of their two limits. Now, I might need to put a special little caveat here because it's pretty clear that the limit of the g cannot equal 0 because that would cause our denominator to be 0 and some really bad things are going to happen. So let's take a look at this single example for this particular video and see if we can make use of these properties. Consider the graphs of the functions f and g given below. Find each of the following limits. Well, we see that a is the limit as x approaches 1 of f plus g of x. Well, if you remember, our property number 2 up above says that we should be able to just split this limit statement up into 2 separate statements joined by a plus sign. And this and this alone should be able to answer the question. And we go into our graph of f of x, and we see as x approaches 1, we move from the left side and we move towards the one from the right side here of the graph, and we end up with a y value that's going to be approaching 2. I'm not saying that the answer is going to be exactly 2. You'll never reach that 2, but that is going to be the limit. Again, you must resist any temptation to think that the answer is 1, because that doesn't have anything to do with the limit. Let's do the same thing for g of x. Here is our 1 here. We're going to approach it from both the left and the right, and we find out that we actually converge upon a destination, right? We converge upon the y value of 1. Even though this doesn't have an actual y value at 2, 2 was still our limit. Even though this had a y value of 1, that can still be our limit as well, right? It's all about what the y values would be coming close to. And of course, I don't think anybody's going to argue that 2 plus 1 is 3, an answer, and that is our limit. Let's take a look at problem B. Now we have a quotient. And so in this particular case, we're going to think that we can attack the problem by using two separate limits divided by one another like this. Let's move that up a bit. And so here we go. We're going to figure out what is, first of all, the limit of g of x as x approaches 3. So this time we're going to our g curve. Here's our 3. We approach from one side, we approach from the other side, and it seems to be that the y value is getting very, very close to, you guessed it, 0. Let's do the same thing for f of x. We approach 3 from one side. Don't have a lot of room here to approach 3 from the right, but I can see that these arrows are going to come together at that y value of -2, and that would be my limit of f. And 0 divided by -2 is perfectly acceptable to leave like that. You don't have to simplify anything on an AP exam, but if we do simplify, we of course would get 0. And that's how you use a pair of these algebraic properties that you see in this box right here to perform some limits graphically. Not too bad, but stick around because some of the videos that follow this are going to address some of the anomalies, like what would have happened if one of those two limits, say, didn't exist? How can you add a does not exist to another number? Or how can you multiply something by a does not exist? So stick around and you'll see what we're going to do about limits like that, as well as limits of our good friends, the composite functions. Until next time, keep studying your calculus, and we'll see you around.